Welcome back. Today we are beginning our unit. We began the unit yesterday watching those Steve Spangler videos. But today we're going to start the notes on our new unit on sound. So up at the top, you've got the word bank and the quick review. It's technically a quick review of the Steve Spangler videos. So pause it, fill that in, and come back. All right, welcome back. Here we go. Light waves are transverse waves, which means that they move at right angles, and sound waves are compression waves, and that means they travel in the same direction. So a transverse wave is like this. A sound wave moves like this. So transverse sound. Sound is all about moving molecules toward your ear. Usually when we hear sounds, they have traveled through the air. Sound does not travel through space because there is no air. Pause it and get that if you need it. Moving on. All right, so sound and light both travel in waves. However, they are not the same type of wave. For a sound to travel, there must be molecules of some type of substance. So it's got to be a solid, a liquid, or a gas. It's got to be a substance that will compress and spread apart to transmit the sound. For sound to travel, there have to be particles that can compress and spread apart. Since there are no molecules of air in space, sound does not travel in space. All right, so now we're going to talk about some of the vocabulary words associated with waves. So first we have wavelength. So wavelength is measured by seeing how far it is from one part of the wave to another repeated part of the wave. Another repeated part of the wave. So it's got to be measured from crest to crest. So from the top over to the top, or from trough to trough. So from the bottom to the bottom. You cannot measure a wave from the top to the bottom. All right, again, if you need to pause. I'm erasing and moving on. So here we have, and if you're doing this online, you might have to open this in Cami or just get a piece of paper and draw this on paper. But we're going to draw a wavelength. I do think it's easier to draw a transverse wave when you put in the node. So we're going to put in the node, that line in the middle, which shows the wave when it's not being disturbed. And then we're going to draw in our nice, simple transverse wave. And then we've got crest, trough, crest, trough. So this is a wavelength and this is a wavelength. What is not a wavelength? This, not a wavelength. Also not a wavelength. This. Because it's from that spot in the wave. If you were going to measure a wavelength from that spot, then you would need to go all the way to here to get to the repeated part of the next wave. Because this is the downswing of that wave, and that's the upswing of this wave. So this to here is not, but this is. Go in that full direction. Next vocabulary word is frequency. Frequency is measured by counting the number of complete waves or wavelengths. So how many wavelengths pass a given point in a certain amount of time. So if we're looking at our three examples here, we've got one wave where it's pretty obvious that that's high frequency and middle and low, but let's really look at it and measure the wavelengths. So here's our first crest, and there's one wavelength. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11 wavelengths in 1 second. So we're assuming that all of these are 1 second. That's 1 second. That's 1 second. All right, so here's one crest, and there's one wavelength, two wavelengths. So that's only 2 in 1 second. And here, that's one crest. So there's one wavelength, 2, 3, 4, 5, 6, 7. That's 7. So the frequency of this is 11 in 1 second. The frequency of this is 2 in 1 second. And the frequency of this is 7 waves per second. So our highest or fastest frequency would be 11, number 1. 7 would be number 2. And 2 would be number 3. All right. As a sound, moves through the air. The particles of the air compress. Compress, get closer together. And rarefact, spread apart. These are the parts of the compression wave. So compression wave is compressions and rarefactions. What are the parts of a transverse wave that we just drew up there? Right, crest and trough. All right, so we're going to draw a compression wave and label the compressions and rarefactions. There are 3 ways to draw a compression wave. Option number 1 is the one that I would really recommend, is the slinky method. You're going to draw places where it's compressed together, places where it's spread apart, places where it's compressed together, places where it's spread apart. That's option number 1. This would be your compression, and this would be your rarefaction. Other options, you could do an up and down line, but it's got to have places where it's close together and places where it's spread apart. You also can do dots. So you're going to have lots of dots and then few dots and then lots of dots and then few dots. Any of those are possible for compression waves. All right, so we have already learned that sound has to have a medium to travel through. It's got to have particles. Sound does not travel if there are no molecules present to vibrate and carry the sound. So I want you to make a prediction. Does sound travel best in solid, liquid, or gas? So write that here on the line. Solid, liquid, or gas. Type that in, whatever you think is your guess. There's no wrong answer except for leaving it blank. All right, so if you were in class, I would do a demonstration where I tap on the table very lightly and then ask you how you can hear it through the air, and then have you put your ear down on the table and tap that same, and you're amazed at how loud it is. So if you're at home, I want you to try that. Tap on the table real lightly, just real light, and then put your ear down on the table and tap again real light and see how much louder it is through that solid table. Right? So sound does not travel as well through the air. We think air because that's how we hear most sounds, but sound actually travels the best through solids. Okay. So the speed of sound depends on the properties of the medium it travels through. So what properties really affect sound? They are temperature, elasticity, and density, or TED. So that's a TQA, TED. Temperature, elasticity, and density are the 3 factors that affect sound. All right, so let's talk about some different materials and what speed they travel. So first, I want you to tell me solid, liquid, or gas for each of these materials. Take a second and do that. Pause it and do that. All right, welcome back. Here we go. Air is a gas. Air is a gas. Fresh water is a liquid. Fresh water is a liquid. Plastic's a solid. Steel's a solid. Did you get that right? Good job. All right, here we go. Sound travels through 0 degrees Celsius air, so cold air, at about 331 meters per second. Warm that air up to 20 degrees Celsius, so about 70 degrees Fahrenheit, and you're looking at 343 meters per second. So there we know that temperature does affect the speed of sound. The warmer the substance is, the better sound's going to travel because those particles are moving faster, and so they can have more energy to carry the sound. All right, what about liquids? Fresh water is about 1480, and salt water is about 1500 meters per second. Darn close, but what does the salt particles do? It adds more molecules. So if you've got more molecules, because you've got the little salt particles floating around water, then the speed of sound is going to be faster. And finally, we have plastic. So there are many different kinds of plastic, but the traditional plastic is about 72 meters per second. And then steel, 5,960 meters per second. Sound travels so well in a solid. And if you think about it, it makes sense. If me and and these markers are molecules, and we're air, we're spread far apart. And so it's hard when a sound is made for this to get enough energy to get over to me, to make me vibrate, and me to get enough energy to get over it, because we're so spread apart. If we're in a liquid, we're a little closer together, and so there's a little easier for us to transmit. And when we're a solid, we're locked together like this. So it's easy to send the messages back and forth. So what do we notice about state of matter? Which one's the best? Right. Solid is fastest. All right. What do we notice about temperature? Right. Warmer is faster. All right. What do we notice about density? A solid of steel is more dense than plastic, but you got to think about it. It's crazy to think about, but once you get too dense and the particles are too locked together, they can't move at all. So density, an increase in density does equal an increase in speed until you get to super dense stuff, until really dense. So like lead, for example, is very dense, and it only has a speed of 1,210 meters per second because it's so dense. So just because something is solid doesn't mean it's necessarily good. All right, so from what you already know about heat, added to what you now know about how sound travels, why do you think air temperature makes a difference? And I've already said this, so hopefully you got it. Why does air temperature make a difference? Exactly, because the particles are moving faster. All right, again, pause it if you need to get that written down. I'm going to clear it and move on. All right, so breaking the sound barrier. The speed of sound is relatively slow. Like compared to the speed of light, the speed of sound is pretty slow. In 1947, U.S. Air Force Captain Chuck Yeager, is that right? Y-E-A? Yeager. That's an E. There we go. Yeager broke the sound barrier. When he reached 293 meters per second, he was traveling at the speed of sound at the altitude that he was flying. When he reached 294 meters per second, he was now going faster than the speed of sound, and he broke national headlines. His plane was actually traveling faster than the sounds that his plane was making could travel. And when you break through that barrier, there's a big boom, and the other people hear, and then everything inside the cockpit gets very smooth because there's no more vibrations. But that's up in the air where the speed of sound is slower due to fewer air particles. So up where the air is rarefied air, up there way high in the atmosphere, speed of sound is slower, so it was easier to break. So it took 50 years, almost to the day, 50 years later, Andy Green, who was a British physicist, came over to Nevada, to the Black Rock Desert, and he was the first one to break the sound barrier on land. In 1997, he drove a jet car. It was a jet-powered car, and he managed to hit a speed of 339 meters per second, and that was 7 meters per second faster than the speed of sound at that altitude. Amazing, right? There are 2 videos under the link of supplemental videos in today's folder for you to watch. We'll watch those in class together, but you at home will have to use the video to watch. So my question is, why did they choose the desert? There's all the reasons, right? Hopefully you thought of some of them. First of all, it's flat, so they don't have to worry about losing or gaining any kind of speed. They can just go. Second, it's an open space. They don't have to worry about running into anything. And finally, it's the desert. It's cold in the morning. And that means the speed of sound was easier to break because it was colder. They did not do it in the heat of the middle of the day. It would have been a lot harder to do because the speed of sound would have been higher in that hotter air. But because it was cold in the morning, they were able to do it. All right, again, pause it if you need to. All right, for this last part, if you're doing this in Cami, you should be able to do this in Cami, but if not, just do it on paper. I want you to draw a compression wave and label. Remember your 3 options, but I really do recommend this Linky, so that's the only one I'm going to do. You're going to do areas where it's compressed together and spread apart. Press together and spread apart. Okay, and label, so that's compression. And this is a rarefaction. Down here, we're drawing a transverse wave, so we need our node. Crest and trough. All right, don't forget to watch those supplemental videos. Watching Andy Green break the sound barrier is really interesting, and it's a nice loud boom, and it's fun to watch. Make sure you do Big Question 18. It's in Monday's folder. Have a lovely day and make good decisions. Bye.